Okay, so if we have a p-n junction, so we've got some p-type region and some n-type region. So we've got a p-type region and an n-type. I don't know how I did that. I suppose my finger was resting on the button. So we've got a bunch of free holes over here. Randomly distributed, a bunch of free electrons over here. And there will be a few electrons in the p-type side, the minority carriers, and there will be a few holes in the n-type side. Those are the minority carriers over there. And then in the near this junction, we have the depletion region where we have a bunch of fixed charges. And on the p-type side, those are negative charges. And on the n-type side, those are positive charges. 1, 2, 3, 4, 5, 6, 7. And I'll show the depletion width is a little bit wider in the n-type region, which would mean that the n-type doping over here is lower than the p-type doping over here. But now we're going to do something different. We're going to apply a voltage. So we apply a voltage like this. Attach a battery or some voltage. So we have, well, okay, first, I can't cover that up. I can cover it up here, but you can't see me cover it up. Without this battery, if I had the board, sometimes I'm used to working with the board and sometimes I want to do something. So without this battery here, there will be a diffusion and a drift current, and they will equal each other quickly, and there will be basically no current flowing across here. And even if we hook up a wire between these two sides, there won't be any current flowing across because those currents cancel out. But if we hook up a battery, and it's just bugging me because my notes, I've written it. Well, anyway, I'm not going to worry about my notes. I know what I'm talking about. If we apply the battery like this, so we have a positive side over here. So that means we've got a plus and a negative voltage like that. It's as if we are adding more holes to this side, and we're adding more electrons to this side. That's what those charges mean. If that seems confusing, if we've got a negative charge here, that repels electrons. So these free electrons, they are pushed away from this negative charge. And over here, these positive holes, they're pushed away from that positive charge, right? They're not attracted, they're pushed away. So we're going to have holes going in. And we're going to have electrons going in because we've attached this battery with this polarity like this, right? And as we bring in more holes, they're going to recombine and fill in some of these fixed charges, and these electrons are going to come in and fill in some of these fixed charges, and we're going to quickly get to the situation where we have, we'll quickly get so we've got p-type and n-type. I didn't leave myself enough room to draw this battery in very well. So we've got a plus and a minus. And we've got a bunch of plus charges here. We're going to quickly get the situation where there's very little depletion left. There'll be some, maybe, depending on how much voltage we apply there. that this depletion region will get squeezed out. And if you want to think of it as reinforcing those holes on the p-type side and reinforcing the electrons on the other side, that's fine. But the end result is we have very little depletion region, and we're pushing holes in this way, and we're pushing in electrons that way, and they're going to combine. So we're going to have electrons that meet up with holes, and when they meet up, they annihilate each other, because a hole is nothing but a missing electron. So if a hole and electron meets, the hole is no longer missing an electron. They're both gone. Poof. And if we have a hole and an electron recombine at this junction, then that means the charge balance is messed up. In this p-type region, there's a missing hole, and in the n-type region, there's a missing electron. So that means we need to bring in another electron over here, and we need to bring in another electron over here as they recombine. And the less depletion width we have, the less of a depletion region like this that we have, the more it easily is for them to recombine. And we're going to have current flows in the same direction as holes, or in the opposite direction of electrons, thanks to Ben Franklin. So we're going to have current flowing through this device. The depletion regions got smaller, and the device is now flowing current. And there will be both current from both minority carriers and minority carriers and majority carriers. So the majority carrier in here is flowing this way, and the majority carrier here is flowing this way. Electrons and holes and meeting up, and the minority carriers are flowing out like that, and the minority carrier is flowing out. So that means we have an electron flowing in this way, and if this hole flows out here, that means we have a hole flowing in here. So we'll have current across this diode due to both majority and minority carriers, but there's so many more majority carriers than minority carriers. So we may have 1e to the 17 majority carriers, and we may have 3,000 minority carriers, right? So the vast amount of this current that's flowing through here will be due to the majority carriers, and it can be a lot of current. And we call this forward bias. And we can have both majority and minority carrier current. And that condition is the voltage on the p-type is greater than the voltage on n-type. That's how I drew this battery. We have a higher potential over here. We have a higher potential on this p-type side than we have on the n-type side, and we call that forward bias. If we do the opposite case, I'll draw on the left side this time. We've got the p-n junction. We have a few carriers of the minority type over here. Come on. and we have those fixed charges in the depletion region. So we start off with negative charges over here. If we connect a battery with a higher voltage on the N-type side, then we've got a voltage over here of a plus and a voltage over here of a minus. That wants to pull electrons out of the N-type side. So electrons want to go out that way, and holes want to go out that way, right? The holes want to escape from here. They want to go towards this negative charge, and the electrons want to go towards this positive charge. So we'll have electrons flowing that way, and we'll have holes flowing that way. That means we've got current flowing that way. But as we pull charges out, we're going to end up making more depletion region. If we're missing electrons here, then there'll be more and more of these fixed charges. And already the fixed charges causes majority carriers to be rejected out of this depletion region. So if we have a majority carrier, a hole over here, if a hole tries to come into this depletion region, and it can, because there's actually pretty big physical distance between these fixed charges. If a hole makes it into here, so if we have a hole that gets all the way over to, what color am I? We had a hole that got all the way over to here, it's going to feel this huge amount of positive charge in the other side of the depletion region, on the other side of the junction, and it's going to get kicked out. And the same thing if we had an electron come over to here, it's going to feel this huge amount of negative charge in the other side of the junction, and it's going to, even though it wandered in here, it's going to get kicked out violently. And electrons are going to get kicked out in the N-type side, and they're going to stay majority carriers. But if this hole wanders in, if we have a free hole that wanders in over to this point, it's going to sense this huge negative voltage on the other side. So the hole's got a positive charge. It's going to sense this huge negative voltage on the other side, and it's going to get sucked across. And as soon as it gets sucked across the junction, it's now a positive carrier. Well, it's always a positive carrier. It's now a majority carrier. And it will be rejected from the depletion region just like this one is. As soon as it crosses it, it's now a majority carrier, it's kicked out. It's kicked out as soon as it gets here. And if we have an electron that makes it over to here, as soon as it gets past the edge of this depletion region, as soon as it gets past here, it's going to get sucked across by this huge positive voltage over there. And it's going to be a majority carrier on this side. So electrons will get rejected out of the depletion region in the N-type side, and holes are going to get rejected out of the depletion region on the P-type side. So that's holes, the majority carrier in P-type are rejected out on both sides. They can't cross the junction to recombine. And that means that there's no majority carrier current. So there's a huge number of majority carriers, and if we put a negative voltage on the P-type side and a positive voltage on the N-type side, electrons are kicked out, they can't cross, and there's very little, there's no majority carrier current. But if we have minority carriers in there, they're sucked across. So minority carriers are still sucked across. So therefore, we have minority carrier current. And that's all we have is the minority carrier current. We call this reverse bias. And we have a very small, tiny negative current. Does that make sense? It's negative. So we have holes that are getting pulled out, and electrons that are getting pulled out. And the current flows in the same direction as the holes and in the opposite direction of the electrons. So we have a current flowing this way instead of what we had here was a current flowing into the p-type region. Now we have a current flowing out of the p-type region, and it's a very small current. And that's called reverse bias. Have a small negative current for reverse bias, and for positive bias, we have a large positive current. I mean, depending on how we define the signs and all. So that depletion width depends on the voltage, right? If we have a large negative voltage, we get a wider depletion region, and if we have a small positive voltage, if we're comparing from the p-type to the n-type region, if we have a small positive voltage, we get less of a depletion width. And so there's an equation for the depletion width, which I'm sure you wanted. The depletion width is 2 epsilon s over q. Well, I already gave you this equation, but now we have the reverse bias on there, V out plus VR. And that's defined so that VR, that's that negative voltage. So this would be the case where we've applied a positive reverse bias. So VR is just the opposite of that. And that just is convenient to make this sign work out. So if we increase VR, as VR gets big, W gets big. And if VR gets small, negative, then we have a forward bias. And W gets small. And might even go away, right? If we applied enough forward bias, that means VR is negative. Then V out minus, if V out equals VR and applied in the opposite direction, then we won't have any depletion width at all. Yeah. Excuse me? 2 epsilon s. So the question is, what's above the Q? I can't believe you can read the Q. So that's not any better. And remember, epsilon s is the relative dielectric constant of the semiconductor times the permittivity of free space. Oops. So for silicon, that's like 11.7. 11.7 times 8.854 e to the minus 14. So there was a question about the last slide. And this is reverse bias. So the depletion width gets bigger if we apply a more negative voltage on the p-type side than the n-type side, and current is squeezed down. It becomes less. And there's a handy equation for that, the diode equation, or the Shockley equation. And that's I is equal to the area of the device, the cross-sectional area of it, and I haven't been showing that, but this is really a three-dimensional device going in all dimensions, and then there would be an area through here, although actually we're worried about the area in the junction. So the area of the device times Q times Ni squared times the diffusion constant of the holes over LP, which is a characteristic length, and the doping, plus diffusion constant of the electrons and a characteristic length in the n-type region, or for the electrons, in the acceptor doping, times e to the v over vt minus 1. And this whole thing right here, for any given device, is a constant for some device parameters. And we call that the scale current. So IS is the scale current, and it equals A times Q times Ni squared times dP over LP ND plus dN ln Na. That's a constant. It actually varies with temperature. There's a problem because it does vary with temperature, but we can deal with that. Ordinarily, the factory gives that to you. So as a designer, it would be a relatively rare situation for you to have any idea what the area of a diode is or to care about it. So it's almost always something that the factory gives you. And with that, we can then write the diode equation as I is equal to IS, scale current, times e to the v over vt minus 1. And IS is often 10 to the minus 12 amps to maybe 10 to the minus, I don't know, 18 amps. It's a relatively small number. It could be bigger, it could be smaller. It depends on physically how big the diode is. So if you're, working with power systems and in cars and stuff, the diode's area might be quite large. If you're thinking about an integrated circuit, then the diode's area could be, fractions of a micron. There's a scale current, and it's a pre-exponential, right? So this IS, the scale current, is multiplied by this exponential relationship. Now, note, this is not IS e to the v over vt minus 1. It's not that. That's a big mistake. If you take e to the v over vt minus 1, that's going to give you a radically different thing and cause you all kinds of troubles if you do this. This is the diode equation. And that relationship if we plot that, we plot current versus voltage. then we get a plot that looks, I can't draw this closely enough to the y-axis there. It shoots up exponentially. The current just increases stunningly quickly with voltage. And often this is about 0.7 volts. So that number will come back and you'll see it a lot. It's often around 0.7 volts for a silicon diode. There's some, it could be a Schottky diode and it might be more like 1/4 of a volt, or a germanium diode is more like 1/4 of a volt. But for silicon diodes, which is most of what you see these days, it may be around 0.7 volts. And the current is just shooting up by the time you get there. You can have an absolutely enormous amount of current. Now, if you apply a very large reverse voltage, very large reverse bias, eventually you'll get to the point where the diode will break down. And that happens at minus VZ. A reverse breakdown. Zener, it's due to the Zener effect or the avalanche. There are different effects, and they occur at about the same voltage, and some devices have more Zener breakdown, some have more avalanche. Avalanche is due to having lots and lots of carriers, and they're all banging in and making more carriers, and the reverse bias is so high that carriers are quickly accelerated, and that causes an amplification of carriers, and you get this huge current. And the Zener effect is by applying such a large voltage that the covalent bonds holding the silicon together are actually broken, and you create a whole bunch of free electrons and holes that way. But it doesn't really matter which is which, and you can't really detect the difference so easily. They generally, it occurs, that breakdown, that reverse breakdown will occur at some voltage VZ. And you can get devices that have that designed. A Zener diode is designed to have a specific reverse breakdown voltage. The reverse breakdown voltage could be minus a few volts. It could be minus 30, 40, 50 volts. It can be all kinds of different voltages. But and you can build devices to have an even larger breakdown voltage if you build them in a certain way. This voltage, this current here, is a tiny negative current. And the forward current is positive bias, or positive bias current, and it can be huge because we've got this exponential relationship. So we'll work through what this means, especially in tomorrow's session. And put in some numbers for there, and you can see if V is negative, then e to the negative number is a very small number. So you have a small number minus 1, that's a negative number, and you'll just have this IS in front. If you have a positive number here, then quickly this minus 1 doesn't make any difference. And you got a large number here, got a large number multiplied by a small number. It becomes a bigger number, and as this becomes a really, really large number, and it's exponential, and that's quick to happen, as because VT is about 0.0258. As this gets particularly large, above say 1/4 of a volt, then this number becomes a real kind of current that you can measure as microamps and milliamps easily, even amps. So we're going to talk a lot more about diodes in this effect, and in fact, transistors are all made up of diodes too. And so the p-n junction is fundamental to how all transistors work. It explains very well exactly what's going on inside a BJT, a bipolar junction transistor. It explains when no current flows in an MOS transistor very well. And the reason current flows in an MOS transistor is because we get rid of the diodes, and there is no more diodes. But we'll talk about those in chapters 5 and 6, I guess. something like that. So there's just a little bit more dimension. We could write an equation for capacitance across the junction. Cj naught over 1 plus Vr over V naught, where Cj naught is area times epsilon s q over 2 in A in D over 2 1 over V naught. And this is given by the factory. So there's a junction capacitance. And if you, as the reverse bias gets large, then the junction capacitance goes down, right? As the reverse bias gets small, the junction capacitance goes up. So by changing the reverse bias, you change a capacitance, and that device is a varactor. So you can change the capacitance by changing the bias on it. There's also diffusion capacitance. Which occurs only forward bias. And that's a transit time, T over the thermal voltage times the current. That's how long it takes to cross the junction. So how long it takes carriers to go across through the depletion region, that's the transit time. Those would be given to you too. But you can make a useful device which varies, its capacitance varies with voltage.
Hey, Professor, can you come back to the previous slide real fast?
That one?
The one where we talk about the diffusion capacitance?
Yeah.
Okay, thank you.
So that's it for chapter 3. If you're in Semi 1, you're learning more about this. And if you're not taking Semi 1, then that's as much as you really need to know to be able to get through electronics. So if we have a p-type region, a junction.
Are we moving to chapter 4 right now?
Yeah, this is chapter 4. It's basically a continuation of chapter 3. But we're going to start talking about the terminal characteristics more. So I already gave you some terminal characteristics, right? These capacitances are terminal characteristics. We're not going to talk about those much more. And the current versus voltage, that's a terminal characteristic. So we're just going to talk a lot more about that now. And we've got a depletion region. Pretty messy drawn device. This structure, this p-n junction, is so common, and we use it for all kinds of things that we have a circuit symbol for it. It's a diode. And this exactly explicitly means that this side of the triangle corresponds to the p-type region, and this line here, where the triangle is coming in, corresponds to the N-type region. So when you see a diode, it may have a symbol like that printed on the package. If it's an LED, there's one way that you know is the high and one way is the low. And I never remember it is. The short leg is the ground or something like that, the low side. So that means the short leg is this side. And when you turn it on, the long leg has a higher voltage. That's this side. And we've got names for those. Anode and cathode. And the current flows this way if we've got a voltage that's plus to minus, a forward current due to that diode equation. So if we I don't know if I want to go through it all again. I don't think I need to. The forward bias. A forward bias means that we have a positive voltage on the anode and a negative voltage on the cathode. Right? We had a positive voltage on the p-type side, and the p-type side corresponds to this end, and the n-type side corresponds to the bar and the short end, or that sharp end of the triangle. The n-type side is over here, and we had a negative voltage. So that's a forward bias condition. And reverse bias condition, where the depletion region gets larger, means that we have a higher voltage on the cathode than we have on the anode. It means we have a higher voltage on the n-type side than on the p-type side, and that chokes off the current, and we only get minority carrier or reverse bias current, which is tiny. And that's these regions. So this region we've got a plus and a minus charge across the diode like that. And in the reverse bias region, we've got a plus voltage and a minus voltage across the diode like that. So reverse bias means the cathode is a higher voltage than the anode, and forward bias means that the cathode is a higher voltage than the anode. It doesn't mean that if you have, say, if we have, say, minus 10 volts here, that doesn't mean that it's forward biased. If we have minus 10 volts on the cathode and we have minus 12 volts on the anode, then it's reverse biased, right? And we could have minus 50 volts on the anode, and as long as we have something less than that, so if we had minus 55 on the cathode, then we would be forward biased. So the voltages could be plus or minus. It's the relative difference across that junction that controls whether it's forward or reverse biased, and whether we get a huge amount of current or not a lot of current. So for forward, bias, we've got a higher voltage on the anode than we have on the cathode, and the equation I equals IS e to the V over, well, let's just say it's a big number. Let me squeeze this in up here. So we have I is I S e to the V over VT minus 1. And so what we get with a forward bias is that the forward bias means, and VT is perhaps 0.0258, right? So VT is a small number, and it doesn't take much of a big number. If we had, 0.5 volts, 0.5 volts over 0.0258 means we have a big number. So we have e to a big number minus 1, which is basically IS e to a big number. All right. That's in forward bias. That's really all we're going to have, because a big V over a little VT is a big number, and e of a big number is a really big number. Minus 1 is still that same really big number, and the equation is basically just this. So we can often say for forward bias, we have that, e to the V over VT. V is the voltage across the diode. In the reverse bias case, we have I equals IS e to the, now we have a negative number, and it could be a big negative number. It could be minus 20, minus 30, whatever. But if we have a negative number, e to a negative number is a tiny thing, right? So it quickly becomes 0. So we quickly have a negative number, minus 1, which is basically equal to, or is equal to e to the, basically equal to 0. 0 minus 1, which is basically, for reverse bias, we quickly get the case where we've got all we have is reverse current. It's a negative IS, the scale current, and we're in this part of the curve, and we don't usually worry about this. It doesn't fit into the equation as nicely, but we've got this negative tiny current, which might be 1 e to the minus 15 amps or something, right? It's a tiny current, but basically we've got 0 minus 1, so we have minus IS. Those are your two. This is one or the other for most cases. If we get very close to 0, then we have to worry about that minus 1, but most of the time we don't have to worry about that. So this chapter is going to look at diodes in terms of a bunch of different models. So we've got some very simple models. We've got models that use this equation. We've got models that use this equation, or that use this or this to do it. We've got models that just say it's like an open or a short. We've got models that get rid of this kind of exponential relationship entirely and let us look at it as a linear device, only over a small region. So this chapter is going to look at how we deal with diodes with several different models, and start looking at actual useful devices and explain how devices work. And by the time we're getting partway through the chapter, you know enough, or you can understand how things like power supplies work, and start to get an understanding of some of the parts of how a power supply works. And you could open up your little wall wart for your little phone or whatever, and actually look at it and understand what it is that you've got and how it's working, at least parts of it. So I think that's kind of exciting to start to understand how things work. So the first model is the ideal diode model. So it's very simple. We've got two cases here. We've got forward and reverse. For forward current, what we're saying is, or for forward bias, we're saying the current is huge, positive. And for reverse bias, we say the current is 0, no current at all. So if we have a device that allows a huge positive current, that's the same as a short circuit, right? A short circuit allows a huge current, right? Any voltage we apply across a short circuit will result in an enormous current, because V equals IR and I equals 0. And so if we look at I is equal to V over R, that equals V over 0. It's quickly infinite, right? We can have a huge current across a short circuit. And over here, we can have any negative voltage across the diode, because it's like a short. I mean an open. So if we've got a diode which is reverse biased, so we've got a higher voltage on the cathode than we have on the anode, then we can replace it with an open circuit, right? That's all we've got to do. And if we have a diode which is forward biased, that means we have a positive voltage on the anode compared to the cathode. Then we replace the diode with a short circuit. Just a wire with 0 resistance. So replace it with a short. So a better way to really say what's happening is that forward bias, that any positive current is allowed. And in the case of reverse bias, it means that any negative voltage the short circuit really can't handle a positive voltage. It's always going to have 0 volts across it, right? But it will allow any positive current. And an open circuit won't allow any current, but it will allow any negative voltage. That's basically a more proper way of understanding what's happening. But sometimes we'll say we're applying a positive voltage. That means it's, in this case, it's forward biased. If it's forward biased, if we're applying a forward positive voltage, it's forward biased. That means we replace it with a short. And so we behave as if the question is there a positive voltage? And then we know it's a short. And is there a negative voltage? We replace it with an open. But really the proper way is saying, is there any current possible to flow through there? And current flows in that direction, right? So if we look at the circuit and we say, yes, there's a positive current, then we replace it with a short. And if we look at the circuit and we say, oh, there's 0 current, there is a negative voltage, we replace it with an open. So if we look at the IV characteristics of that, what we have is a device which handles any negative voltage, or can allow any negative voltage and any positive current. It actually can't handle a positive voltage, and it can't handle a negative current, right? The ideal diode model only does forward bias where it's on, reverse bias where it's off, and replace it with a short or an open circuit. Now, often we use these words on or off. So forward bias means on. And that's often in terms of this region of like zero resistance. We say that's forward or on. And reverse bias is this region over here. And we will use, or I will, and people often use these terms interchangeably. Forward bias is on, reverse bias is off. It's as if it's a switch, and we can use diodes as a switch, but we use these interchangeably, on, off, forward, reverse. So this characteristic of a diode, this is a highly nonlinear thing, right? It's got 3 different regions. It's highly nonlinear, especially right here. It's an exponential relationship. That's just, it's a wild thing, that exponential relationship. And here we have a device that's totally linear. It's piecewise linear, but it's totally linear. There's no curvy bits in this at all. And because of that, that makes analysis, it can be really, really quick and really, really easy. And it can be surprisingly accurate. It's not very hard to do even better. But to actually use the diode equation can be kind of a pain sometimes. So solving it perfectly, unless you're doing homework, is a real pain. And usually you would let a simulator do that for you to actually solve the diode equation. And SPICE and things doesn't add a whole lot of more parameters than what's in the diode equation. There's a few things that it'll add depending on what you're doing, but it's pretty close to that. But so let's do an example. So if we've got a circuit, we've got forward again and reverse, and the circuit looks like we've just got a voltage source and a resistor, call it 1K. Say we got 10 volts here, and we've got a diode, and we'll say we've got that means we have a positive voltage across here, right? We've got 10 volts on this power supply. And we've got a resistor, so that's going to limit the amount of current, but it doesn't change the voltage. It means we have a higher voltage on the anode than the cathode, right? And we replace it with the short. So I can just redraw it. And I replace the diode with a short, and we've got 10 volts and 1K, and we've got a short. So it's easy to find the diode. voltage and current, the voltage across the diode, and the current in the diode. So the voltage across the diode is equal to 0, right? And the current in the diode is just 10 volts divided by 10K, or 10 milliamps. And that's remarkably close to what the real answer would really be. It's not quite that, but it's remarkably close. So if we had the reverse bias case, same circuit, same diode configuration.
I have a question.
Go ahead.
Where did you get the 10K from?
Oh, it's 1K.
Okay.
And 10 over 1K is 10 milliamps anyway. Thank you. So now we have, we've got 10 volts here in 1K, and we've got a negative and a positive. Oh, let me switch that sign here. Well, I'll just say it's here. Got negative 10 there. That means we have a higher voltage on the cathode than we have on the anode. That means it's reverse biased. And we replace the reverse bias diode with an open circuit. And we have a diode voltage. And we have a diode current. And now the diode voltage is just the same as the voltage on the source over here. We've got that voltage right here across the source, so we've got minus 10 there. The diode voltage is now minus 10. And the current is 0 because we got an open circuit. Two cases, those are the only two choices. So the relationship is for any negative voltage, we have no current, and for any positive current, we have no voltage, right? So here, in this case, we've got a negative voltage from anode or cathode to cathode, and that negative voltage means that we replace it with a open circuit, and we have no current, and the voltage across here is just the voltage across the source. Over here, we have a positive current. We've got current flowing in because we have a higher voltage on this side than this side, so we have a positive current. We can replace the diode with a short. We have no volts across the diode, but we can find the current from just these two components, and we've got 10 milliamps. So analysis is that easy, but of course we make it harder because that's what we do, right? We'll make it harder, but it's still basically fairly simple analysis. If we move the diode over here, and we're looking at an output voltage, and we've got a resistor of some kind, and we've got a diode voltage that's defined that way. But by writing it this way, I'm not saying that the diode voltage is always positive. I'm just saying that we have, we've defined VD as plus to minus across the diode that way. And we've got some input voltage, which varies the sinusoid. I'll draw it this way. I'm debating whether to draw a sine or a cosine. I can't really draw cosines very well, I think. So we have this input voltage here, and it's swinging. Some of the time it's positive. Here and here it's a positive voltage, so we have a positive voltage at that time. At that time, this diode is forward biased, right? When we have a positive voltage, and we'll have current flowing through here. And then it goes negative, and when it goes negative, the current turns off, and it can support any negative voltage, and it just turns off. So we've got two different chunks of time to look at. We've got the forward biased portion. That's when the circuit would look like this. We replace it with a short. And we've got R, and we've got VI, and V out. The diode's a short. And that means that I, or V out, the output voltage will be exactly the same as the input voltage, right? All of the input voltage is going to drop across this resistor, and we're going to see exactly the same output as we have input. And the current will be VI over R, and V out will equal VI. And if we draw the waveform of that, then we're going to get the positive going parts of that sinusoid, because this region here is forward biased. Right? Whenever we have a positive voltage on there with the ideal model, we've got a forward bias. And for the negative bias time, so the reverse, we replace the diode with an open. So we've got an output voltage that's 0 because we have no current. Right? We've replaced the diode with an open. No current flows through the circuit, no current flows in the resistor, so the voltage across the resistor is 0. And we have an output characteristic for the negative going part, which is just 0. And that's for this chunk of time. For that negative input voltage, we've got a reverse bias. The diode's turned off, it's open, and no current flows through at all. And if we draw the total so V in and V out versus time. So V in, we've got like that. For the output voltage, we'll exactly have the same as the input, but whenever the input goes negative, it just is 0. The output's 0, and this is a rectifier. This circuit here. We've got a rectifier circuit, a circuit that is blocking the reverse current, and you have a 0 output, and allowing the forward current to go through. And this will turn AC into DC, right? It'll change alternating current that swings from plus to minus. It'll change it to current that's only plus. Doesn't make it a stable current yet, but this is the first step to making the power supply, is if we've got an AC current coming in off the wall. First thing we want to do is run it through a rectifier and turn it into a voltage that doesn't change anymore.